This video is going to talk a bit about, we'll give you some hints on really how to draw bending moment diagrams without numbers. And this is really going from a deflected shape to a bending moment diagram. So, just briefly, we'll discuss why. Why would we want to do this? Well, you'd ask, Lucas, don't you have access to a computer? Isn't this something which is better to just program it and spit out over and over and over again? Well, that's true in an office setting, but oftentimes as an engineer, you have to go on site, you have to look at a problem, and you've got to make up your mind on the problem and understand the problem sort of on the fly. And so you don't have time to go back, run a computer program, come in. You need to sort of develop that engineering intuition, and you need some tools in order to do that, to sort of check yourself. And that's what we're going to show you here. And the reason that you've been taught bending moment diagrams really from, an applied load, set up your equilibrium equations, determine, what your shear force and your bending moment is with respect to a distance. And you set this up algebraically, and that's a really good way to learn it. However, it's slow. So what we want to do is think of, can we go from it, instead of going force to shear force diagram to bending moment diagram to deflection, can we go the other direction? Can we go deflection to bending moment diagram? And so the reason that we think about deflection is, that's often an easier concept for us to visualize. If you've been walking around the world, you've seen how things bend and move, and so you can get a good intuitive sense for it. And so if you understand how things bend and move, then you can think, well, what are those, what are the internal forces which are generated from that? So with that, we're going to jump in and really give you the first few, the rules sort of that help you navigate this type of, plotting bending moment diagrams from deflected shapes. And they're not terribly difficult rules, but they are, really important to keep in mind. And if you can apply these and then plot your bending moment diagram on the tension side, then you should be a long way away a long way there towards being able to do this repeatedly. So our first rule is that a fixed support has no rotation. So we'll write that down. So, this is our classic fixed support here. If we are to push on it, well, it's going to bend, but the very bottom has to stay at 90 degrees. So if our dashed line is our deflected shape, right at the bottom, it's still at 90 degrees. It hasn't rotated, and it hasn't translated, and that's just the definition of fixed. And so that's always a good thing to think about when when you're drawing your deflected shape. The other thing to keep in mind that if we don't have a rotation there, we're likely to generate a moment. And so if you think about cantilevers, a cantilever like this, well, that's just this turned on its side. If you put a point load here, we'll draw the bending moment diagram in red. Well, yeah, see, we don't, our deflected shape looks like this. So we'll draw our little 90 degrees. It's just going to, deflect downwards. And, we know from, cantilevers that we have a moment generated there. So that's sort of a pretty good rule to kind of keep in mind. All right, so that's our first rule. So again, pretty straightforward, similar stuff that you've learned already. Our second rule is that displacement, compatibility, has to be maintained. So what do I mean by that? Well, I think just like with the fixed support, it's good to do this with an example. So in fact, what we'll do, we'll just start calling these. We'll call this rule 1, just so we can put little ones with the diagram. So we'll call this rule 2. So with rule 2. Say we have a corner, and that corner is at 90 degrees. Well, if we rotate this corner around, say we rotate it down, by some degree theta, well, that corner has to stay at 90 degrees to each other. So so we'll call this be our little 2. So what that means is that if you've got a, so say that you've got, we'll fix one end, and we'll put another end on a roller. And if we're going to rotate this around, well, we know that we've got to stay at 90 degrees here. We've got to stay at 90 degrees here. This is our first rule. This is our second rule. Well, a good way to do this is just sort of draw our... So say we move the support this way. Just help the light there a little bit. Well, we know the support's going to go there. We know that, well, that's going to rotate this around. So we'll draw that. We know that this has to stay at 0 coming out. So so if our corner is sort of fixed and at its orientation here, and the support here, the fixed support's there, well, then that means that the only way we can accommodate these rotations is for this beam here in the middle to bend. And so that's kind of what our deflected shape looks like. So you can see how these rules can get applied, just relatively simple rules where the bottom so fixed supports, you can't rotate them. And if you have a joint or a corner which is fixed, well, or at 90 degrees, that has to stay at 90 degrees as you rotate that through. And then so the only other thing which can move are the flexible parts of the beams in the middle. So that's our second rule. So now, these are really our first 2 rules are really around displacements. Our third rule is pretty simple. At a pin, the moment equals 0. So that's, I mean, we're quite comfortable with that, right? So, if you've got a simply supported beam and it's got a point load on it, well, our moment diagram will just look like that, where at the pin support, so you can think of this as, at a pin or at a free end, or and we'll just sort of separate that up over here. So at a free end, it's the same thing. Now, if we had a pin support somewhere in the middle here, well, remember the beam is continuous over there. So we don't, just because there's the presence of a pin, that pin has to be internal. So let's say either, internal. So the caveat, pin must be internal or at the end of the member. All right. So again, this is consistent with what you've already learned. So a lot of these rules are really just a reiteration of how you've already learned how to do bending moment diagrams. You might not have thought of them explicitly, but that's really all they are. All right. And so rule number 4, we only have 2 more rules to go. So rule number 4, at a corner, moments are equal and opposite. And that is in order to maintain equilibrium. This is really Newton's third law. And then the final one, and then I'll sort of show a little example for both 4 and 5, is that moments, we'll call that reverse. So you can think about reverse as they are changing signs at points of contraflexure. You can think of that points as contraflexure as like, this is the same as, an inflection point. So you might have thought of an inflection point in math where, if you've got a curve which kind of is keeping the, and it's where you change curvature. So, you've got a curve that's going this way, and then all of a sudden it goes this direction. Well, the little red dot here is our inflection point. That's where we change curvature. So change the sign of our curvature, really. So, we have sort of a positive curvature, and then we switch to a negative one. And right here where we have this inflection point, if this were a structure which had a moment, we'd find that the sign of our moment would change between this side and this side at this point here. So just showing a quick little sort of description of this. So say we have we've got a little frame here. So single bay frame. One end is fixed, one end is pinned, and it's got a load here. So we'll bring our, we'll just redraw it over here for our bending moment diagram. So we'll say this is, this shows us sort of rule 4 and 5. It really shows all of these rules here. So, fixed support has to be 0, displacement compatibility has to be made. So we'll just say, this is, all rules. Example. So how would we tackle this problem? Well, what's the bending moment demand? Relative bending moment demand. Well, the easiest thing to do is just start with the deflected shape. And so when doing the deflected shape, you want to just, you can break it down into pieces, and you can think about, well, what do you know? Well, we know that down here at the bottom, that we have no rotation, no movement. Also, here in the corners, well, these have to stay at 90 degrees. So looking back so if this is going to be our bending moment diagram over here, and then we will do our deflected shape on top of this one. Well, what else do we know? We know that at a pin, the moment is 0. So we know that our moment's going to be 0 here. And we know that, well, we expect, at our fixed support, we expect there to be some moment demand here. All right. So say we looked at this as a little bit simpler problem. So say we only looked at, this column or this pin. So if we move, it over here, all right. So we will move our point over here. We'll move another point over here. Well, actually, let's do, so, looking at this column, maybe not the best one, because you think sort of, pin, or, it's technically fixed pin. Yeah, so actually, let's come over here. So if I'm going to start on this column, and I'm going to displace it over here, well, I know the base has to stay put. And I'm going to have, some 90 degree. Well, it's going to want to, is it going to bend, like that? Well, it can't, right? Because my base is grabbing it. I can't rotate the base, so I know that it's got to come out sort of, straight out of the ground. And, well, it's going to kind of do this S-shape thing here, right? And you can, you can grab a little stick and you can see that. So, if I have this little stick here, I'll hold my left hand still, and I'll just move this. So you see, I've got a fixed end. Look, it's putting in that little S shape. If I let's see if I can do this as sort of a little pin, so that it can kind of rotate in my left hand and fixed. There you go. We'll pin it like this. Try to get the shadow out of there for you. Maybe I'll do it on. Yeah. So if it's pinned and then it's grabbed in my right hand, you see it just sort of has a single curvature. It just kind of bends in sort of this loopy shape. So, well, we can expect it to bend, kind of like that. So, that's what our columns look like. All right, so now the next rule is, well, we've got some curvature. It's sort of tilting, this way over here, but that has to stay at 90 degrees. So, well, that means that our column's going to sort of be pointing, so it's going to be pointing kind of like that. And this has to stay at 90 degrees. It's going to sort of point like that. And that's our deflected shape. So yeah, that's not quite there. So yeah, we've got that. So see if I can again just sort of get you a little bit of a little demonstration here. So if it's going if it's going this way, you can see that it's going to curve up, and then if we put it the other way, and we We'll just hold this still. Let's try to bend it there. You can see it wants to kind of curve down. And that's all because it's trying to maintain that 90 degrees. So, this way it's curving down. Go the other way, it's going to curve up. So that's why we've got, we'll curve up over on the left and curve down, and then we've got some point of contraflexure. So all we have to do now is kind of plot our bending moment, and let's just plot on the tension side. So if this beam is bending this way, the tension side is over here, 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 here. So I've just put a little T where we expect tension to be. And so, well, we know it's 0, and we know it has to come up to some point. Well, there's only one load here. So if you were to think about, like our cantilever, well, one load, well, your moment's just going to increase linearly with distance away from that load. So just going to be, P over P times, your distance x. Because there are no other loads here, there's no other shear, so we wouldn't expect any other moment. So we could say, on the tension side, we know that we're going to have a linear response. So again, think if you've got a point load, you're going to have linear moment. If you have a uniformly distributed load, you're going to have a parabolic. And that just goes back to your shear rules and your bending moment diagram rules. All right, so that's that side. Well, let's do this column over here. Well, we know that we've got some tension force. We've got some tension and we've got some bending here. So that's our tension side there. And we know we've got some bending there. And we have a point of contraflexure. So our curvature direction changes here. So, and that will say it's about mid-height. And again, we only have the one force pushing in, so we only have the one moment. And so, and then our rule, we're at a corner. We have to maintain equilibrium. Well, let's just do that. So if it's, we've got a moment here, well, we've got to have sort of equal and opposite up here. And a moment here, you got to be equal and opposite there. And then you just connect them. And this is what our bending moment diagram looks like. All right. Well, let's do another example. And let's do one just with beams. And we'll do two more examples, and hopefully that will help clarify this even more. So we've got this example here. We'll just do a So just a single point load. All right. Well, first thing we want to do is we want to sketch our deflected shape. So if you think about, and if you ever struggle, start, just like we did over here, break it into the pieces that you do understand. If we look at just this, a simply supported beam, well, we understand a simply supported beam. See if I can hold that here. It's just going to deflect. If we push on it, it's just going to deflect like a banana. And so, well, we expect it to bend something like that. Well, now on the other side, well, if it's bending here, and we're continuous over this piece, and then it has to come, we know it has to come back down to 0 over here because it's connected. Well, it wants to kind of, one way, if it wasn't connected, so if this was just a free end, it would just bend up, you know, and go on kind of for forever. So maybe I can show you that on this little model. So a little model here. So if we just bend down, you see it would just want to kind of, you know, bend up and just keep going up. Now, if we restrain that bottom piece, well, it's got to come back down then, you know. So say we put in a roller support here. You can see, well, it's going to bend here, and then it bends up a little bit, and then it comes back down. So it doesn't stay straight. It does bend, but it just, you know, it doesn't bend nearly as much on this side. So we know it's got to come back down here, and we'll say, well, it's going to bend a bit like that. So our deflected shape is going to look something like this. So where if we call this D1 and we call this D2, we know that D1 is going to be greater than D2. All right, so let's start thinking about other parts in order to get us to our bending moment diagram. So we know the tension side. It's always good to just kind of mark, you know, where the tension side is. It's going to be above the line here. So as we draw our bending moment diagram, well, we know that we'll be sort of down here and up here for the different spans. The other thing to keep in mind is that, you know, look, the direction of curvature changes. So there'll be a point of contraflexure somewhere kind of in here. And it's, if you look, it's probably about there, you know. That's our inflection point. And that makes sense, right? And that's the only way we can get the moments to sort of switch sides. All right, then what else do we know? Well, we know we have a point load here. So if we look at just this half of the, you know, from just this side to the support, well, what is the, you know, what would the moment look like from there? Well, if we look just, you know, just from the point load, well, the moment is just going to increase. So if we take a little free body diagram cut here, well, we know that, you know, the moment is, in order for this to be in equilibrium, is just going to be this times the distance away. So it's linear. So we know that it's going to go linear. Now, and again, it's going to be linear here, but we've got to get, we've got to cross over at some point. And then we got to think about, well, what does our span look like over here? Well, over here, the only thing that, you know, the only loading sort of on this side is really just going to be the shear force from this reaction coming up. And we know that we've got a free end here, so the moment has to come back down to 0. And so, well, that's going to be linear there because it's just going to be this shear force as we go through. So and then we connect that up. Again, we've got a point of contraflexure. That's where our moment is going to be 0, and that's where we switch sides. So that's you can put your happy beam and your sad beam there as well. So like I said, if you've got a point load, you know that you're going to have linear distributions of your moment. We'll do one more example and then wrap this up. So let's just do a very similar example, but we'll do it with a uniformly distributed load. right, so first thing we think about is, well, what's our deflected shape? Well, we know, and again, start with the parts you know. Well, we know what the deflected shape looks like for a simply supported beam with a UDL. So we know that it's going to bend down like that. Again, if this reaction wasn't here, if this pin wasn't here, and this was just sort of a free end, sort of like a diving board, well, then the deflected shape would just continue going up. But because it's here, well, this part which is going up has to get pulled back down. So we know our deflected shape is going to be something like that. And just like with the point load, I mean, it's hard for me to put a UDL on this, but just like with the point load, we know that the span which has its the load applied is going to have much higher deflections than the span over here. So you can see that it does start. So if I just put my my pen right here at the end, you can see it does move up, ever so slightly. The span which is load is much higher, but because we've got a higher deflection, we're going to have a higher moment. And so you can think of that as our relative moments there. So for the bending moment diagram, again, what are the things that we know? We know at the free ends where we've got so either at a free end or at the end of a member which has a pin support. Well, we know the moment has to be 0 here. That's one of our rules. Just over here. That's one of our rules. At pin or free end, 0. The pin in the middle, because the beam's continuous, we can support a moment across there. But at either end, well, there's nothing to restrain the rotation of that beam, and so we know we have to be 0 there. We know if we're going to plot on the tension side that in this span, well, you see this is the tension side here, and then the tension side there. So we know right away 2 of our points, and we know that we've got to be down here on this side and up here on the other side. We know which is good because we've got a point of contraflexure. So at some point we have to be able to transition across. All right, so and again, if we're ever confused and we're confronted by a part that we don't know, a whole system that we don't know well, let's look at the parts that we do know well. So we know that our bending moment diagram for a simply supported beam with a UDL looks something like that. Well, in order for us to have any bending over here, we know that there has to be some bending moment being applied at this point. So it can't be 0. So this value has to be up somewhere negative in order to get this to bend. So that means, well, let's redraw this a little bit. So we know that it's going to come up there. We know that we have a lot more bending on this span than this span, so this bending moment value will be higher than over here. So we know that that is wrong. So this is probably pretty good here. So we know it's going to go parabolically, and we know that we have to have some sort of negative moment over here in order to be applied. And then in terms of, how does it come across there? Well, it's going to have to come down to 0. And so our bending moment diagram will look something like that. So I hope those examples and some of those rules were helpful and informative. Again, the best thing to do is sort of draw the deflected shape as best you can. Look at your rules, know things that, like, when you've got your moments coming back down to 0. And then really think about the structure and think about, well, if you're going to have bending, well, you need to have a moment applied. And so yeah, and that's it. And I think maybe just one more tip is anytime where you've got a support or a discontinuity, where you're going to have a big shear force, you're likely to have a big sort of peak in your moment diagram. All right. With that, we'll wrap this up, and good luck on your MDLS activity, where you're going to be doing a whole series of these with the little models.